Hi, I'm Chris Kanish, and this is CS361, Systems Programming. Today, we're going to be talking about the nitty-gritty of how virtual memory gives you the capabilities it does when it comes to mapping physical addresses onto virtual addresses and how we handle page hits and page misses. Let's get started. So last time we were talking about why do we need virtual memory? Why is it a hard problem? What's the design space that we can be choosing from different strategies to accomplish our goal from? But today we're going to be talking about how are we actually going to solve that problem and what are the nitty-gritty, specific problems that we're going to need to solve to actually create a good working virtual memory. The first of these problems is the addressing problem, where because we're going to be using physical addresses and virtual addresses, we don't really know where our address 400,000 or any given address is actually going to be stored at runtime. Our user level process has no idea what that address is. The compiler has no idea what that address is. That's a challenge that we're going to need to solve, but virtual memory more or less very straightforwardly solves that problem by saying, listen, you, the user level process, you, the compiler, are never, ever going to need to know where your stuff is in the actual chips of memory stored in the motherboard. You only need to know this fake address, and we, the CPU and the operating system, are going to do the translation for you. So this relocation process of talking about keeping things in different places, but then actually mapping them to the same place, more or less solves that problem. The next one is the protection problem. Remember that the operating system is in charge of isolating the different processes that are running on the computer from each other. So if I haven't been given explicit access to your memory, I should not be able to access it. And again, this is something where the idea of virtual memory kind of gets the job done. If we're translating every single memory address such that I can never talk about raw physical memory, I, as an individual user level process, can only talk about the memory that I was given access to by the CPU and the operating system. I don't even have the words to describe somebody else's memory. If I have a view of the world that's just my own, that's good for me is that it makes my life simpler, but it's also good for everybody else because then I can't mess around with their memory. So by having the virtual memory system as the way that we're going to handle multiplexing access to the memory that requires you to translate every single memory access, you solve this isolation problem. And finally, we have this space problem where sometimes there's going to be more processes that are using memory than we want to. Sometimes we're going to have to just keep things organized in a given way. And sometimes we're going to have less memory available to us than we actually have for individual processes. And this is where we're going to have page eviction, which in modern systems isn't that important, but it's still a fundamental component of the design of virtual memory. And so it's really useful to talk about and think about here. But remember that this running out of space, limited space problem is almost always not a real pressing concern in modern systems. We'll be seeing the page fault and the page miss process happen a lot. If you remember from the book reading, it said a whole bunch about how we're using virtual memory as a cache for the disk. And while that's true, we're not so much using the disk as a place to store things that we had already previously saved into memory. We're much more often going to use the disk as the initial place to receive something from, and we're going to use demand paging, we're going to see in a little bit, to make that process work a little bit faster and a little bit simpler and a little bit better. So just a few definitions here. When we have an address space, this is every single process is going to have its own address space. It's going to have virtual addresses. And these virtual addresses are just numbers. They start at some number, say 0, makes a whole lot of sense. They go up to some really, really big number, say n-1. Typically, if we're going to be addressing these, byte addressable. If we go up to the number 2 to the n-1, we need n bits to talk about that address. Now, when we have our physical addresses and our virtual addresses, every single process has their own effectively identical copy of the virtual memory address space. There is no such thing as virtual memory. Virtual memory is an idea that we're going to use to organize our physical memory. So if I have a program that starts at hex 400,000 and you have a program that starts at hex 400,000, so I have one and you have one and somebody else has one, all of those addresses are going to map to completely different places in memory in the physical chips that we're actually using. The hardware is going to be doing the job of translating this stuff for us. But even though the hardware, that memory management unit, is going to be doing the translation for us, how the translation happens, what you go from and what you go to, is going to be the job of the page tables, and that's managed by the operating system. So as I mentioned on the previous slide, this solves our relocation problem. The CPU will always do it, and this solves our isolation problem. You can't access anything that you don't have a mapping for, and you don't control your mappings. The operating system controls your mapping, so you're not going to be able to read other people's memory. The main focus of this week's content is the page table. This is going to be the data structure that keeps track of a whole bunch of information, and we're going to see what a lot of those specifics are next week. First thing that we're going to talk about are these 3 different pieces of information that are associated with each individual page table entry. And one of them is kind of implicit. Remember that when we're talking about L values and R values, this is getting a lot more complicated than it has been in the past. There's implicitly, whenever you have an array, just stack them. Here's one, here's another one, here's another one, here's another one. And where you are in that address space of that array has to do with what your index is, right? So if I create just this thing right here, and it's got a valid bit, and it has a page mapping number. This one has a valid bit and a page mapping number, a valid bit and a page mapping number. Yeah, if we look at it, there's 2 pieces of explicit data being saved there. But the really important other piece of information is where you are in the offsets of this page table itself. We know that page table entry 0 maps to this one. We know that page table entry 1 maps to this one. We know that page table entry 2, 3, 4, 5, etc. Right? So this is something that we need to keep in mind. It's not always going to be in the drawing, whether we're talking about virtual address spaces or physical address spaces or anything. But whenever we talk about an array of contiguous chunks of information, we're almost always going to have an index into that array, even though we don't have to store the index itself. We just know that if we know where it starts and we know how far away something is, we know what the address is of that new thing as well. So our page table entries, for the purposes of today's lecture, have a valid bit as to whether or not it is a currently valid mapping, and then the mapping itself. So we can see that page table entry 0 is not valid. There is no page table entry mapping there, so it's unallocated. Conversely, you can have a valid page table entry that has a mapping that goes into physical memory, and it is a valid page of memory. That is something which has been allocated to the process and is actually resident in memory. So if we're going to be accessing something that is a valid page table entry, it's going to be relatively straightforward. So we're going to have a virtual address. We're going to find which page of memory that virtual address is in. Let's say it's in this page, page table entry 2. We see that it is valid, and we see that it maps to virtual page 2 stored in physical page 1 in this case. The memory management unit will translate this virtual address to a physical address within that physical page on the main memory of the machine. The page table is managed by the operating system. The actual mapping itself, the process of mapping over the course of an instruction, is done by the memory management unit. That has to be done by hardware that's on or connected to the CPU rather than being done by the operating system. Because remember, the operating system is not running at all times. When I'm running user-level instructions, the operating system is not running its own instructions. So this mapping itself has to be visible to and understandable by the CPU itself. Now, that's a page hit. That's kind of all she wrote. When we get to the end of that process, that is relatively straightforward. The other flavor that we have here is something which is allocated. So this one right here is allocated, but it isn't actually valid right now. It's an invalid mapping. because it goes to the virtual memory that is stored on the disk rather than stored in main memory. So when we want to access something that is a virtual address that points into this invalid page table entry, but it is something that is allocated, then we have what's called a page fault. Remember, interrupts, traps, faults, and aborts. This is a recoverable error that was caused by an instruction just trying to do its job, and then it sees, oh, hey, I was trying to load from this specific address, but the page table entry is invalid. The CPU detects that that page table entry is invalid. It causes an error and says, hey, operating system, fix this problem for me, put that page of virtual memory into physical memory so that I can actually do my job and run this instruction to completion and run it successfully. Now here, if we're thinking about RAM as a cache, 261 style, this is a cache miss. We were using the memory as a cache for the disk. The disk has the real, true copy of that information, and we couldn't find it. So like any other cache miss, we're going to have to go out there and find it, then find a place to put it. So that's exactly what we're going to do here. So we have this page fault. This is an exception. It traps into the kernel. The kernel says, hey, I'm going to find some way to take this information that's stored on the disk and store it into physical memory so that this load instruction or store instruction or whatever have you can actually run to completion successfully. In some situations, when you have filled up your RAM, you are going to have to evict a page of memory. In most modern systems, we don't do too much of this page eviction because remember, disks even now are so much slower than our main memory that our programs are going to just grind to an effective halt if they're trying to move information in and out of the hard drive or wherever it's being stored to get jobs done. Usually you don't have to do that process, but it is something that we want to keep track of. This is going to be relatively uncommon in modern systems that you have to do eviction. The page fault process will still happen quite a bit even if we aren't doing eviction. This is one of the most important concepts that I want you to take away from today, is that even though we're using the page fault mechanism and the way it's described in the book has to do with evicting a valid page table mapping from physical memory and then taking our virtual memory that's on the disk and putting it in its stead, that eviction process isn't always going to be necessary. It's going to be very, very common for there to be free space in memory, but because we're doing demand paging, as we're going to see in just a moment, we don't pull things into memory until we actually need them. Because we don't pull them in until we actually need them, we're going to rely on this page fault mechanism to do the regular expected loading that we want to do when we start running a program or when we start reading information from the disk. So to get back to that page fault mechanism, when we find an invalid page table entry that is allocated, we know that we have to do, say, some eviction. So maybe we're going to take virtual page 4 and we're going to move it out to the physical disk. We're going to write whatever changes have been done to that physical page 4 out to disk, and we're going to move virtual page 3 from the disk into that physical page 3. And here's the other important part. We're going to restart that instruction. So we basically assume that everything is going to be fine. We're going to assume that a page hit is going to be the correct thing to happen. If we don't get a page hit, if the instruction starts and it grinds to a halt saying, whoop, I can't actually do this load because it's loading from an invalid page table entry, the operating system is going to be alerted via an exception. The operating system is going to say, okay, put that instruction aside. Let's run the operating system procedure that's going to pull this virtual page in from disk, put it into RAM in some place, fix up the mappings, and then rerun that instruction. And then it works. We're just going to restart that instruction and not do anything special because we restarted it. We're just going to run the instruction again. And when we run that instruction again, we're going to get a page hit. And again, I can't stress this enough. This is one of those really tricky things that honestly, it took me a couple of semesters to wrap my head around the fact that this is how it works. I think the biggest thing that I personally had a problem with, because I remember, from the way back when you'd be running 4 megabytes of RAM and you run out of RAM and all of a sudden things are really, really slow, but you kind of could keep doing like playing your game or whatever it is that you were doing. That's not nearly as common a use of the page fault mechanism as this just garden variety, I want to load something. There is no load this piece of memory in for me that you use on an everyday basis. You probably could find some way to explicitly force the operating system to pull a page of memory in. But far more often, what we're going to be doing is just saying, you know what, I'm going to find that mapping. I'm going to set that mapping up like these gray elements here, and I'm just going to wait for the page fault mechanism to pull it in for me. I'm going to do this demand paging, this lazy loading, where you say, I'm not going to touch it, I'm not going to deal with it until it's actually needed. Just like the last time we talked about lazy loading, this is the same exact system building trick. If we do something before the last possible moment that it's needed, we don't know whether it was actually going to be needed at all, because we can't see into the future. We can't know what is going to be needed by this individual program. So if we don't know what's going to be needed, maybe this thing that we spent all this time pulling in isn't actually needed. The other nice thing about this page fault mechanism as the main way for us to bring things into memory is that we can do this super lazy loading. We can say, all right, well, if I want to run Bash, or I want to run Chrome, or I want to run Word, or whatever it is I'm trying to run, I don't have to actually load the entire process into memory. I don't have to load everything from that ELF executable into specific places in memory. All I need to do is set up the mappings. I set up a bunch of mappings, and then I let the page fault mechanism do all the work for me. We don't have to do anything besides set the mappings up and let the page fault take care of it. This is what I was talking about earlier on, where the virtual memory mechanism allows us to simplify the design of our entire loading process and just have it all work on the page fault mechanism. Another aspect of the page fault mechanism is that while a lot of memory is loaded in from disk, right? For instance, we're pulling in the text section of a Bash program, or we're going to pull in a bunch of textures for a game or a map or something like that. We're pulling them off of individual chunks of binary data that's stored on the disk. Sometimes, like for the stack and for the heap, we don't need stuff that comes off of disk. But what we actually do is we still use the page fault mechanism. Whenever a process says, hey, I need 500 megabytes of space, the operating system is like, okay, why would you ask for that much at once? That's usually not very common, but sure, you want 500 megabytes of space? It creates 500 mappings to a special thing called the zero page, and it just says, okay, you know, I gave you 500 megabytes of memory. It didn't actually give them to you, but it is actually going to just create those mappings to a special thing called the anonymous page or the zero page, which says, okay, this page doesn't actually exist. They don't actually have 500 megabytes of memory. I'm just going to tell them they do. And when they actually write to it, I'm going to say, oh, well, okay, well, if you wanted to write to this memory that was all zeros, then I'm going to actually give you your own unique page. Until then, that memory is brand new. Brand new memory is all zeros. All zeros is all zeros, whether it's in my program or your program or somebody else's program. And so every page that's all zeros points to the same physical page in memory that is the zero page. So that zero page is super, super useful. The last thing I want to talk about here is the memory management benefits that we get from using virtual memory in this way. So not only can we map things all onto the same thing for the zero page, we can map different things that are going to be functionally identical across two different processes. If I want to share memory between two different processes, I can do that by having one physical page and then two different virtual pages that point at that same memory. They don't even have to be using the same virtual addresses. I can be using virtual address 123 in one process. I can be using 456 in another process. And if they both map onto 10, 11, 12, I don't care. Like, as long as they're the same bytes and they're in the same order, I don't care what their address is, as long as I know that I'm using it starting from here and you know that you're using it starting from there. The other even better reason for us to be able to share memory is when we're sharing read-only memory, like the text of a program. When we're sharing the text of a program or we're sharing the text of a library, we don't need to change any of that. Remember, we load those things in read-only. If we load them in read-only, we can load them wherever the heck we want within the virtual address space of that individual program, of that running process. And then we simply map them onto the physical memory that comes from some other file, like the glibc shared library. This allows us to save a very substantial amount of RAM when we're running lots of different copies of programs that are all using, say, the same version of the C standard library that's dynamically linked in. And remember, when we use less memory, we can use the faster memory for more different important things in our working set. And that allows us to run our processes faster, which we always want to happen. So that's the end of what we've got for you today. Thanks so much for watching, and I'll see you next time.